Next up is friction. We're talking about opposing motion in our discussion of forces, and we'll get right to it. I'm going to answer hopefully these questions. What is friction? What are types of friction? What is this, a coefficient of friction? And given some situations, how can we look at friction and answer some questions about it in ways that might show up on an assessment? All right. Vocabulary is just basically friction, and then a couple different types, static and sliding friction we have here. So first question is simply, what is friction? It's a force that opposes motion. So kind of like the normal force, we don't really notice the normal force unless there's a weight pushing down on something. So the table that's in front of me, for example, I don't really notice that it's pushing up on something until I put something on it. And once I put something on it, since it stops, then there's an opposing force, and that normal force opposes the weight. Friction is kind of the same thing, but in the side-to-side direction. So anytime we have two surfaces touching, there's going to be friction between the two. We typically don't notice or pay attention to that friction until we actually start trying to push on something kind of in the side-to-side direction. So friction is the force that opposes motion. What causes it? It's going to be due to these little tiny irregularities in the surface that make it not particularly completely smooth. On Earth, probably, ice would be the best example of something that is closest to being frictionless, but there's really no such thing particularly as a completely frictionless surface because of the irregularities on there. So some things have more friction than others. Things like oil and ice tend to not have a lot of friction. Other things like sandpaper, rubber, and we'll talk about those in a minute, do. And again, it would have to do with the way that it looks if we could magnify it up. So again, some surfaces are smooth, they would have low friction. Some are rough, they would have more. In particular, with this unit, one of the things that we want to pay attention to is the idea of there's a static friction and then there's this sliding friction. So static means that something is kind of still. You've probably experienced this before, and you could do it right now if you have your computer, your Chromebook in front of you. It's kind of the amount of push that you would need to get something moving to begin with. So if you took your hand and kind of put it on the side of your Chromebook and started pushing, you'd notice that if you pushed a little bit, just a tiny bit, it's not going to move. But eventually, if you push hard enough, you're going to get some kind of motion that's going to be able to move. So that amount of friction that you had to overcome just then, that was considered to be the static friction. Once you get it moving, there's still a push back against you, and we call that the sliding friction. So the static friction is when an object's at rest. The sliding friction is when the object is moving. And the amount of friction an object has during these two times is not the same. The static friction is always going to be greater than the sliding friction. Again, you've probably experienced this. Again, you could experience it just with the stuff right in front of you. It is harder to get something moving than it is to keep it moving. Once you get something moving, you just continue pushing it. And again, you can notice this probably with your Chromebook or anything else in front of you, that it requires a little bit more force to get something moving than it does to keep it moving. So static friction is always going to be greater than the amount of sliding friction. When we're looking at diagrams, again, oftentimes we've got all these different forces that are labeled, whether it's on an incline like on the left, or if it's flat like we have on the right. The friction is always going to be parallel to the surfaces themselves. So if we went over the inclined plane diagrams like you've seen earlier, we have this parallel force going down the ramp, and the frictional force is going in the opposite direction. But again, both of these lines are parallel to the surface of the ramp. And the same thing over here. If we have an effort force or an action force that's going to the left, the friction force is going to be going back to the right. In this case, you can see the way this one's drawn, they're equal and opposite, so they should cancel each other out. Again, that doesn't mean that it's stopped. It simply means that it wouldn't be accelerating. So oftentimes when we're pushing something, if it's not speeding up, then the amount of our action force is going to be completely balanced out by the friction force. Again, that doesn't make it stop. It just keeps it from speeding up. So we're always going to see the F with the little f, that's our frictional force, going in the opposite direction of our action force, and it's going to be parallel to whatever surface that we tend to be on. Okay. Typically, the friction will equal the applied force, or this effort force, until the object starts to move. So if this was a really, really heavy brick or something like that, it might require our push to get longer and longer and longer before it ever started to move. And what we would see is that these two arrows are going to increase proportionally along the same way. Again, if it's stopped and we're pushing and pushing and pushing until it moves, the two arrows are going to be the same. In order to get it to move, we would need this arrow to be just slightly bigger than the frictional arrow. There's a point at which this arrow over here is not going to grow anymore. That's the amount of friction we would need to overcome to be able to move. So what determines the amount of friction? Effectively, a couple things. It's the weight of the object pushing down onto the surface and the material of the object, which kind of determines how smooth or how rough it is. Sometimes people think the surface area kind of determines the amount of friction, but that's really not the case. It's more the weight pushing down. So both of these objects in this diagram would have the same weight. And so even though the one on the left has more surface area touching, it's not going to be harder to move or easier to move. So it's really just the weight of the object and the material itself. Getting a little bit more mathematical, although I don't think we're assessed on any of these things too directly. There's a formula on your formula sheet that looks like this. There's a big F with a little f, that's your frictional force. There's a big F with the N, that's your normal force that has to do with the weight of the object. And then there's this Greek letter mu. So this Greek letter mu stands for the coefficient of friction. And so the coefficient of friction differs for different objects. And it's simply a ratio of the frictional force that it has divided by the normal force, which is the weight. Basically, what this means is the bigger this value is, the more friction it's got. Because again, the U is going to be proportional to the frictional force. So if it's harder to move something, then this value is going to end up being higher. So again, depends on the material. The greater the mu, the greater the frictional force. So you could kind of think, if you had these things to choose from and you're trying to push them across wood, which one would have a greater mu? Cork, rubber, sandpaper, or cardboard? You'd want to think which one would require the most force to be able to actually get it to move. And we want to say if they all had the same weights as well. So the one that would be the hardest to move, if we went through and looked at these, would be rubber. I have a cat meowing. Go, shoo. Rubber would be the hardest one to push for its weight, followed by sandpaper, cork, and then cardboard would slide across pretty easily for its weight. So again, if we wanted to rank the coefficient of friction of these things, again, the greater the coefficient, the more friction it's going to end up having. So if you wanted to get a good workout, probably pushing rubber tires across a surface like this will be much harder to do than if you had an equal amount of wood or an equal amount of sandpaper or an equal amount of cardboard. Those other things would slide across easier. How could we measure the static friction? I'll say it's simple. You'd need something to actually register on a measuring device, but it would just simply be the amount of force needed to get an object to begin sliding. So if you could measure, particularly pulling something, if you had a spring or something along those lines, how much effort, how much resistance was there in actually getting the object to move, and you could register that and measure that, and that would tell us the amount of static friction that a particular object actually had. So the amount of friction is the same amount of force that it takes just to get it to move. So again, we can't really measure static friction without pushing it. And so once we get it to move, then we know that we've overcome that amount. And so that's going to give us an idea. So some example problems, if we had an object like this and we're asked some questions about it, if we had a 260 Newton crate, it's at rest on the floor. It needs 79 newtons to start it moving to the right. And you were asked to draw a free body diagram showing all the forces on the crate. And then could you find the coefficient of friction between the crate and the floor? So our first thing to do would be to think about all the forces that we have on here, because we've got a force going up and down. So we've got something going down, we've got something up, and we would have something going left, and we would have something right. So think about where everything goes. The weight should be going down. The normal force is in the opposite direction of the weight. And if we're moving it to the right, then we would need to have an effort force or an action force moving to the right, and the friction would be opposing that moving to the left. So if we drew it out and added all the numbers, it should look approximately like this. Now, again, the normal force and the weight should be, notice they're going to be equal numbers. So if the weight's 260 newtons, then the normal force up is 260 newtons. And if our effort force or action force to the right is 79 newtons, then the amount of friction that we have going to the left is also going to be the same amount if it's not moving, or if that's the amount it took to just get it moving. If you were asked to find the coefficient of friction, which again, likely something we don't necessarily need to do, you could go to your reference sheet, and this is the formula we have, and we'd be solving for mu. So we would need to know the frictional force and the normal force in order to do that. And again, those were given to us effectively in the problem because the frictional force is the same as the action force, and the normal force is going to be the same as the weight. So if we know the weight, we know the normal force. and likewise up here. So we could just plug those numbers in. So again, the frictional force was 79. The normal force is 216. You could divide those out to be 0.3. Again, this is just a ratio of how much friction is there compared to the weight. And again, the higher the number, the harder it's going to be to move. So in summary, main points, friction simply pushes against our motion. So if I'm pushing to the right, friction pushes to the left. There's two types. Static is when an object is at rest. Sliding is when it's in motion. And the amount of static friction is always going to be greater than the amount of sliding motion. All right, so again, to move an object, you've got to push with just a wee bit more force than the amount of friction it has. Technically, if an object had 80 newtons of friction and you pushed with 80 newtons on it, it's not going to move. But once you just barely got over 81, it would start to accelerate and you'd be able to move it. Now, again, once it starts moving, you don't have to keep pushing it that hard to keep it moving, because once it starts moving, it's going to require less force. So again, the initial push to get it moving is going to be greater than the continuing push to be able to keep it moving. And again, you've probably experienced this when you've moved things around before. And we'll stop.